Good morning, everyone, and welcome to our deep dive into a critical yet often unseen component of the Internet, the DNS root servers. We've all experienced the frustration of a slow or unresponsive Internet connection, but few consider the foundational elements that keep it running smoothly. The Domain Name System, or DNS, is often called the phone book of the Internet, translating human-readable domain names like google.com into machine-readable IP addresses. At the very top of this hierarchical system are the DNS root servers. They are the initial point of contact for nearly every Internet query, acting as the ultimate authority for top-level domains. Today, we'll explore what these servers are, their vital role, and what happens when this invisible backbone, the very foundation of our digital world, faces challenges or cracks. Understanding these issues is key to appreciating the Internet's resilience and the constant vigilance required to maintain it. So, what exactly are DNS root servers? Contrary to popular belief, there aren't just one or two servers. The DNS root zone is served by 13 logical servers, often identified by letters A through M. While there are 13 logical servers, these are not 13 physical machines in a single location. Instead, each of these 13 logical servers is actually a network of hundreds of physical server instances distributed globally. This distributed architecture is a cornerstone of the Internet's resilience. Operated by various organizations, including ICANN, VeriSign, and university research groups, these servers collectively manage the very top of the DNS hierarchy. They hold the pointers to the top-level domain, or TLD, such as those for .com, .org, or country code domains like .uk. Without these root servers, the entire DNS resolution process would grind to a halt. Let's trace the journey of a typical DNS query to understand the root server's pivotal role. When you type a domain name like example.com into your browser, your computer first asks your local DNS resolver. If the resolver doesn't have the IP address cached, it then queries one of the 13 root servers. The root server doesn't know the exact IP address for example.com, but it knows which server is responsible for the .com top-level domain. So it responds by directing your resolver to a .com TLD server. Your resolver then queries the .com TLD server, which in turn directs it to the authoritative server for example.com. Finally, the authoritative server provides the actual IP address, allowing your browser to connect to the website. This multi-step lookup, initiated by the root server, ensures that your request reaches its destination efficiently. Given their critical function, DNS root servers are constant targets for various threats. One of the most prevalent issues is distributed denial of service, or DDoS attacks. These attacks overwhelm the servers with a flood of malicious traffic, making them unavailable for legitimate queries. We've seen several significant DDoS events impact root server operations in the past. Beyond deliberate attacks, misconfigurations or software bugs within the server software can also cause widespread issues. A simple error in a configuration file could propagate across the entire root system. Lastly, physical infrastructure failures, though rare due to the extensive redundancy, could theoretically impact specific server instances. This could include power outages, hardware malfunctions, or even natural disasters affecting a data center. Each type of issue presents a unique challenge to the stability of the Internet. What would actually happen if a root server or several were to fail? The immediate impact might not be a total Internet blackout, thanks to caching. Most DNS resolvers cache information, so existing connections and frequently visited websites would likely continue to function for a period. However, any attempt to resolve a new domain name or a domain whose cached entry has expired would fail. This means new websites wouldn't load and new services couldn't be accessed. A prolonged or widespread root server failure would gradually lead to a cascading effect where more and more domains become unreachable as their cache entries expire. Essentially, the Internet would slowly but surely become unusable for anyone trying to access anything new, leading to significant economic disruption and communication breakdowns globally. The Internet's foundation, once cracked, would slowly crumble.
While catastrophic, complete root server failures are rare, the system has faced significant challenges. One of the most notable incidents occurred in October 2002, when 7 out of the then 13 root servers were subjected to a massive DDoS attack. While the system demonstrated remarkable resilience and no widespread outage occurred, it highlighted the vulnerabilities. More recently, in 2016, a series of distributed denial-of-service attacks targeted critical DNS infrastructure, including elements that interact closely with root servers, causing disruptions for major websites and online services. These events serve as stark reminders of the constant vigilance required. The Internet community continuously learns from these incidents, strengthening defenses and improving protocols to ensure that such attacks do not cripple the entire global network. These attacks underscore the importance of ongoing security research and collaboration.
Fortunately, the Internet community is well aware of these risks and has implemented robust mitigation strategies. The primary defense mechanism is anycast routing. Instead of a single physical server for each of the 13 logical root servers, anycast allows multiple physical servers, often hundreds or thousands, to share the same IP address. When a query is sent to a root server IP, it's routed to the nearest available physical instance. This global distribution means that there are now over 1,700 physical root server instances worldwide. This extensive redundancy ensures that even if several instances or entire regions go offline, others can continue to serve requests. Furthermore, extensive caching at various levels of the DNS hierarchy reduces the load on root servers and provides a buffer against immediate impacts of outages. These layers of defense are crucial for maintaining the Internet's stability. The landscape of DNS is continuously evolving, and so too is the resilience of root servers. Future developments focus on several key areas. Enhanced security protocols like DNSSEC or DNS security extensions provide authentication for DNS data, preventing tampering and spoofing, thereby fortifying the trust chain from the root. The increasing adoption of encrypted DNS, such as DNS over HTTPS (DO) and DNS over TLS (DOT), helps protect user privacy and prevent eavesdropping on DNS queries. There's also ongoing research into more decentralized DNS solutions, potentially utilizing blockchain technologies, which could offer even greater resilience against centralized failures. The global community, through organizations like ICANN and various research bodies, is constantly working to anticipate new threats and implement innovations that will keep the Internet's foundation strong and adaptable for decades to come. In conclusion, the DNS root servers are far more than just obscure pieces of hardware. They are the bedrock upon which the entire Internet rests. They are the initial guides for billions of daily queries, connecting us to information and services around the globe. While they face constant threats, from sophisticated cyber attacks to potential misconfigurations, the multi-layered architecture, widespread geographic distribution, and ingenious solutions like anycast routing provide a robust defense. The Internet's continued functionality is a testament to the foresight and ongoing dedication of the engineers and organizations that manage this critical infrastructure. As technology advances, so too must our vigilance and innovative spirit to ensure that the Internet's foundation remains resilient, secure, and accessible for everyone. It's a collective responsibility to understand and support the mechanisms that keep our digital world connected.